This is part 3 of the video on statistical inference. It is kind of hard to squeeze an entire statistics course, maybe even 2 of them, into 3 videos, but hopefully this is the last of them. Will include all the material. So this is by far the most valuable of these techniques, because as I was saying, 2-dimensional slices of a multi-dimensional picture are not adequate, and they are quite misleading. So it can be quite misleading. So let's look at how multiple regression works. I'm still using this houses data set. And what we really want to know is, how do each of these factors contribute to the price? Because plausibly, each of these might be related to the price. If we had to state up front what we thought the relationships would be, I would think that bigger houses sell for more money, so more square feet leads to more higher price. The age of houses, probably the older the house is, the less valuable it is. In some parts of the country, like in Dubuque, when you get really old houses, sometimes, especially if they were kept up, they become quite valuable. But in the Southwest, well, same thing's true there. There are some old parts of Albuquerque where it could be quite valuable. But generally, I think older houses don't sell for as much money. Features is a bad measure, but generally you would think that more features would contribute to the higher price. I know Albuquerque somewhat, and I never thought of the Northeast as being a particular important area, but I guess the idea is the Northeast, I think our newest suburbs maybe is more valuable, but somebody thought somehow the Northeast was worth separating. It was never clear to me that that would have an effect on the value. Custom built, I would think, are more valuable, and the corner I would think is generally less valuable, except there's 2 things that go on. Being on a corner, you usually get a bigger lot, and that's worth something, but corner has traffic, and especially if you have kids, probably not real desirable. So in any case, plausibly, all of these might affect the price. To do multiple regression is not difficult. You go under Analyze, except you go to Fit Model, and you put price as what you are trying to explain. And these are the factors that you're using. I'll just take them all right now and put them in here. And you run this model. You get a bunch of output here. The effect summary is not a bad place to start. It's going to show you which of the factors you put in your model are most important, and and a measure of the confidence that that signal is coming out from the background noise. So you can see square footage is the most important variable by far. P-value very close to 0, meaning that you can pretty safely say square footage is affecting the price. Custom built, also low p-value, not nearly as influential as the square footage, but seems to have some importance. Age seems to count for something. Notice the p-value is still less than 0.05. Being on the corner, now we're getting up there. P-value of 11%. Maybe it's not having an effect. Maybe we can't really tell. The Northeast and features, certainly we can't tell. It shows the residuals, and I will talk about this at a different time, but residuals can be quite revealing, because what you are looking for in residuals is randomness. Anything other than a random pattern suggests that there's something systematic that you can put in your model. Technically, you violate one of the regression assumptions if there's any kind of pattern here. And there is one that's being violated here, because when I look at this, the pattern I see is that the residuals seem closer to 0 at the low levels of predicted price, and they seem to be fanning out. It's kind of a cone shape. And that violates a technical assumption, is that the linear model that we just fit, the variability of the residuals should be constant at all levels of the independent variables. Technically, what this is called is homogeneity. I'm spacing out the term. It's a hard one to say anyway, but well, it'll come back to me later. But we're actually violating one of those assumptions here, and there are ways to deal with that. The real problem when assumptions are violated is not that you have to throw out the analysis, is that you can actually improve the analysis because there's something systematic going on here. This is not a serious violation, though. So again, we have an R-squared measure, 0.83, basically saying 83% of the variation in price is accounted for by this set of variables that we used in this model, all these variables. The root mean square error is an important term. It's basically saying if you did predictions out of this model of the price for individual houses, on average you would be, not really on average because you're taking squared errors and taking the square root of it, but it's roughly speaking the average deviation of the predictions from the actual. So the errors that your model would be making would be on the order of about $17,000. So based on an average price of the house of about $106,000, that means your errors are on the order of almost 20, like 16% of the predicted price is an error. So the model's far from perfect, and actually notice there's only 68 houses, so we're going to come back and look at that in a minute. How did we lose? We had 117 houses. Why did we lose so many? But before I go on with that, let's see what the model tells us. The analysis of variance table is just the mathematics is there to produce this table, but it's never anything to look at when you're doing multiple regression. So let's see if we can just get rid of it. Here's the model. Here you see this expression. This is the prediction expression written out. It basically has all the same numbers that are in the parameter estimates. There's the intercept, the square footage coefficient, the age coefficient, features, all of these coefficients appear up here. When you look at the parameter estimates table, first thing to look at is the estimates and whether they're positive or negative. So square footage, positive, contributes to price. Age being negative means higher ages, older houses, less valuable. Features, more features, higher price. Northeast, negative. Custom built, positive. Corner, negative. These are only point estimates, so you might want to go across to the confidence interval. I mean, the $63.72 for each square foot, the confidence interval, 95% is between $53.50 and $74 per square foot. Clearly, far from zero, we know it's a positive influence, and it's somewhere in that range, is what we would say with 95% confidence. Age, the confidence interval is from minus $733 for each year of age to minus $11 each year of age. So $11 wouldn't be very much of an effect, but it's still a negative number. So in fact, we're pretty confident that it's a negative effect of age. Notice features could be from minus $3,460 per feature to plus $4,111 per feature. Anywhere from a negative to a positive means we really can't say with any degree of confidence that features has an impact, because it could be negative or positive, potentially somewhat sizable, but if I can't say if it's negative or positive, there's not much I can say about features. And that derives from the fact that features was measured very badly here just by counting features, and garages and dishwashers are not the same thing. Northeast could have a large impact, could be anywhere from minus 11,000 to plus 8,000. Custom built, on the other hand, notice it's all positive numbers, anywhere from $4,000 to $26,000 extra for being custom built. And the corner, anywhere from a large negative number to a modest positive number. And notice this corresponds to the p-values. The fact that the confidence interval for corner goes from negative to positive associated with the p-value being greater than 5%. The 95% confidence interval for custom built is all positive. The p-value is less than 5%. Northeast, negative to positive, p-values higher than 5%. Features, negative to positive, p-values higher than 5%. And both the top two are either positive in the first case, negative in the second, and both p-values are less than 5%. So the hypothesis test here is just the inverse of looking at the confidence interval. It's the same information displayed in a less intelligible way. And the way these p-values are actually constructed is each of these estimated coefficients has a standard error associated with it, which is the idea of the central limit theorem, but taken to a much more technical and mathematically derived estimate of how much variability we can expect in this coefficient if we were to keep taking random samples. And the t ratio is saying how many of these standard errors is each of the estimated coefficients away from 0. So we're literally testing hypothesis that there's no relationship between each of these variables and the price. And in each case, we're measuring how far away from 0 that estimated coefficient is, measured in standard errors. And when the t ratio is high, the p-value is low. And when the t ratio is small, the p-value is high. And so that's the way the hypothesis test is done. The confidence interval is the same information, just arranged in a different way. So let me say a few things about what you would do at this point. If this were the model you were going to end up with. Some books, actually many of them, would say that you should drop these insignificant variables, take features in northeast out of the model. I actually don't subscribe to that. I think that the only reason to take things out of the model, and it could be applied in this case, is that if you've got too many variables compared to the data points, then it becomes very difficult for the computer to be separating the influence on price of each of these separate variables. And so reducing the number of variables could be good. On the other hand, and this is what I think is more important, is when you remove a variable, you can start changing the influence of the other variables. Everything's going to readjust. And you're looking for a truer model, not a less true model. And it's very hard for me to say that by removing two of these influences and letting some of the other variables pick up those influences, it's hard for me to say that that's a truer model. It seems to me that it's probably less true, because now you're having the other coefficients represent the whatever minor effects features in northeast might have been having. So I think it's worth stating that we don't have evidence that the features in northeast are just too noisy a variable to really be able to say anything about them. But it doesn't mean we shouldn't have them in the model. They're still imparting some influence, whatever it is. It's just very noisy. We could use this model for prediction. If you were doing that, you click on the red arrow and you would go to Save Columns, and you could save the prediction formula, which would save this prediction expression and calculate it for each of these houses. I'm not going to do that yet because I don't think we really have the best model by any means. Before I change the model, let me also explain what's shown up here in each of these plots. These leverage plots are really not useful to look at unless you have a fairly small sample, which arguably we have here. Most data sets you work with, you're going to have much bigger samples than this, and these pictures aren't going to add anything. What they are two-dimensional slices that are constructed the following way. The square footage leverage plot basically says, let's build a different model where we try to explain the price using each of these variables, but not square footage. So it uses custom-built age, corner, northeast, and features. It builds that multiple regression model. It then says, let's look at the residuals, what's not explained, what's left over. Let's plot those residuals against the square footage. If there's a significant relationship, it's saying square footage should be in the model because it explains some of what's left over. But we already knew that square footage has a significant impact on price. You can tell it right here from parameter estimates. So we're finding out the same thing. The p-value just appears here. Age, is it a significant influence? And notice the horizontal line is at the average, so it's really testing hypothesis that the average residual, that there's a relationship between the residuals and age. And if there was no relationship, the blue line would represent it, and the shaded area is actually a 95% confidence interval. And if it doesn't overlap the blue line, then you have found a significant effect. This is really close, but p-value is less than 0.05. Let's look at one where it's not. Here, they're almost completely overlapped. Once you include all the variables except for features, if you look at the residuals and plot them against features, you're not seeing any relationship. So it's just noise. But we already know that from the p-values. The only value of these leverage plots is that they do allow you to have two-dimensional slices of a multi-dimensional picture, and so you can identify things like this, these outliers. Both of those are row 89, so row 89 is seeming like a significant outlier in a number of dimensions, which might be worth investigating further. But generally, the leverage plots are really telling you the same thing that you already have in the parameter estimates table. So the parameter estimates is most of what you want to look at. Now, what happened to the houses? Why did we lose almost half of our data set? Well, let's go back and look at the data. Oh, look at age. It's a bunch of missing data. Well, when you run a multiple regression analysis, what you're really asking the computer to do is not do a bunch of fit y by x analyses separately. You're asking it to take into account all of these variables simultaneously and give the way to interpret these coefficients is the effect of each square foot on price is $63.72 after taking into account the age, the number of features, whether or not it's in the Northeast, whether or not it's custom built, whether or not it's on a corner. So it is not simply doing a graph of price versus square footage and ignoring the others. It's taking into account the variation in all the other variables. Any variables that you don't have data on, like age, you can't include in the model, so it's just leaving it out. So a lot of the age of houses are missing. So what I would recommend doing in this case, with that much data missing, it's a small data set to begin with. We don't want to lose almost half of it due to missing data. If you go to save script to redo, to where it says relaunch analysis, a simple thing to do here would be under the red arrow up here, just click what's called informative missing. Now jump will include all 117 houses. But if the age is missing, I think it's going to replace age with its mean value, and it's going to create a new variable, an indicator that age was missing, and put that in the model as might that have a significant influence on the price. Now notice square footage is still the most influential variable. Age and missing coded, so it's including two things together, the age where we know it and whether or not the age was missing, and that has now become the second most important variable. 117 data points are in here. The R squared is a little lower than before, but that's probably due to the fact that we have a lot more houses in our data set, so there's a lot more variability. Go to our parameter estimate. Notice when you look at age, there's two different ones, and they're both quite significant. Age, where it's missing, is included the mean. So pretending that those houses that we're missing ages on had the average age of houses in this data set, each year of age is decreasing the price by about $466. In addition, houses where we're missing the age sell for $13,803 less on average. So it's significant to be missing the age of a house. It's a bad sign somehow. Now, why that is, I don't know. I'm not sure how this data was collected, but I'd like to then know, why is the age? But remember, this comes from newspaper ads, so it's quite possible that it seems to me that if they didn't put the age in the ad, it probably means that the age was a problem. It was probably old. Probably not, even using the mean was probably not a good description. But without knowing anything more, we might say, let's replace the age, the missing ages, with the mean of all the ages. But the fact that it's missing has such a negative effect is probably an indication that old houses, they didn't want to say how old they were. And it has significant impact on price. In fact, that minus $13,803 kind of offsets the $14,718 positive effect of custom built. Notice all the variables are statistically significant with the exception of features, which is still performing very badly. Northeast is not significant, although it's very close now, 0.05. Also notice it has a positive coefficient now. So in the last model, it actually had negative, but once we've included more of these houses in, all 117, and once we've included age, and whether age is missing, it seems like the Northeast is tending towards having higher values than other parts of Albuquerque. P-value technically is above 5%. You'll notice the confidence interval goes from a very small negative number to a fairly large positive number. It includes 0, which is why the p-value is greater than 0.05, but not by much. So this model seems to me superior to the other one. It's explaining a lot more. I will mention that there are other ways to handle missing data. The informative missing is a really useful thing to have because JMP will automatically create this, what's called a dummy variable, an indicator variable for whether age was missing. And it puts in the mean value for what was missing. If it's a nominal variable, I think it puts in whatever the most common category is for the nominal variable. There are more sophisticated ways to handle missing data. So in fact, under tables, actually not tables, I think it's under analyze. If you go to screening, explore missing values, you could pick them all. It's the only one that's missing anything is age, but if you pick that, 49 of them are missing. And you actually have a couple of ways that it will impute values. Instead of just putting in the mean, it can actually build a model to try to explain, trying to predict, in a sense, what the missing value is from the other variables that you have data on. So there are a couple of imputation methods where JMP will actually try to create numbers to put in for the missing values. And it will still, that's an alternative because it won't then flag them as missing anymore. Once you do that imputation, it will replace in the data set the missing values with the imputed values. And when you run the model, it'll use those imputed values. So sometimes imputation can be an extremely useful way to do it. The more common way, and I think really the safer way to do it, is just to use the informative missing, because then it's flagging for you. Is it important that the age was missing? And clearly here, that is quite important, has a fairly large impact. Okay, a couple of features of this that I want to talk about, though. You may have noticed that I put in Northeast, custom built, and corner as continuous variables. They're measured as 0 and 1. And so when you get to one like Northeast, it's saying if it's in the Northeast, value 1, you are adding $7,459. If Northeast was equal to 0, 0 times this means you're not adding anything. If it's custom built, you're adding 14,718. If it's on a corner, you're subtracting 10,936. If it's not on the corner, 0 times this, you're not including anything. If it's not custom built, 0 times this, you're not including that in the model. So look at the way it's written out here. If custom built is 0, you multiply 0 times that number. If it's 1, you include that number. Very straightforward interpretation of what the coefficient means. In reality, of course, custom built is not a continuous variable. It's a nominal variable. So let's just go back and change custom built to nominal. And then let's take our second model and let's rerun that. Just want to make sure it's appearing as nominal, yes. If you carefully compare, well, let me do it. There's that one. And that one. And here they are side by side. If you look down the p-value column, you'll see they're identical numbers in the two. If you look at r squared, it's identical. The root mean square error is identical. All of these numbers are identical. The only numbers that are different is the intercept has the same p-value, but 27,684, and here it's 35,000. When you get to custom built, it's 14,718, and over here, custom built is minus 7,359 with the same p-value. In fact, these are showing the same thing. It's just that the one on the right is harder to interpret because the interpretation is for a nominal variable. What it does is show you all the values for that nominal variable except for one. It leaves one out. It leaves one out for mathematical reasons that we don't need to worry about here. I'll show you how to get it in a second. This is saying if it's custom built equal to 0, meaning it's not custom built, then you subtract $7,359 and 0.206 compared to the average of all houses. And if it is custom built, you add 7,000. So whatever makes, in fact, to see that, if you click on estimates to expanded estimates, if you have a categorical effect with k levels, in this case 2 levels, 0 and 1, there will be k minus 1 parameters, only one parameter. Expanded estimates let you see them all. And well, okay, I don't know how to manage all the windows here, but take a look at what we get with the 0 and 1. The 0 and 1 have the same number, just opposite signs, and they add up to 0. So, in other words, if it's not custom built, you subtract 7,359. If it is custom built, you add 7,359. How much influence does it being custom built versus not custom built have? Well, the difference between these two is twice 7,359, which is in fact 14,718. So all it's doing is taking that 14,718, which is the difference between custom built and not custom built, and it's breaking it into two separate pieces, how much additional for custom built and how much less for not custom built. Clearly, it's harder to interpret when you put it as a nominal variable. So usually in JMP, you should tell JMP what kind of variable it is and give it the right coding. The one exception is when you're doing regression analysis and a variable is measured as 0, 1. Putting it in as a continuous variable, even though it's not really continuous, makes it a lot easier to interpret. You look at this estimated coefficient, and that's the effect of it being a 1 rather than a 0. Otherwise, if you put it in as a nominal variable, you have to remember that you're missing one value up here in parameter estimates. You have to ask for the expanded estimates, and then you have to interpret each of these as the difference compared to the average. So the difference between it being 0 and 1 is these two effects added together, which is twice as large. A lot harder to interpret. So I just find for nominal variables that only have two values and they're coded as 0, 1, full jump into thinking it's continuous because it's just a lot easier to interpret what you get. Okay, let's take a look at another important feature here. Let's add a new column. Let's call it size in square meters. Instead of measuring square feet, let's take the square feet. There is an exact, it's not exactly 3 feet to a meter, but this will work just as well. Let's just assume if we divide by 9, we'll get to square meters. A meter is a little more than 3 feet, so there's an actual conversion. It's a slightly different number, but this will be good enough. So size in square meters was simply square feet divided by 9. Let's take this model that we just ran, second model, and let's add in our new variable, size in square meters. Now, if you think about what I'm doing here, oh, and wait a second. Let's change custom built back to continuous. Don't need to confuse things more. If you think about what I'm doing here, I already know the size of the house by square feet. Putting in the square meters, which was derived from square feet, is not creating any new information. On top of it, it's creating a mathematical problem because the matrix algebra behind deriving this model is basically going to say, you've given me the same information twice, I can't use both. And in fact, it has zeroed out one, and it's marked the other one as biased. So it has basically said, uh-oh, something went wrong here. You gave me too much information. I can't use all these variables because 2 of them are identical. So it was a mistake. This is known as multicollinearity. It's identified the problem for us. So JUMP's pretty smart. It'll catch that kind of mistake. But all you have to do is add to this a very small random component. Let's just add a standard normal distribution. So we're adding to things that are on the order of hundreds of square meters a random number from -3 to +3. That's what a standard normal looks like. We've just perturbed it a little bit. The size in square meters now is slightly dislodged. And you can see this if you put the size in square meters versus square feet now. Before, it actually would have been a straight line. It's very close to a straight line, but not exactly. It's actually somewhat random. If you can see how it's jumping around a little bit. I've introduced a very minor random influence. Let's go ahead and add size in square meters in. Because it's not exactly the same information, JUMP actually doesn't know there's an error. It actually does this analysis, thinks it's okay. But you have a problem that's known as multicollinearity, and it shows up here in a classic way. If I look at square feet, it seems to have a positive influence, but the p-value is suddenly now really high, 0.78. And the size in square meters has a negative influence. It's almost the same exact number. It's only slightly randomly perturbed, and it has a really high p-value as well. The symptom of multicollinearity is the things that are closely related the computer will force one to have a really big positive effect and the other one to have a really big negative effect, because it's looking at almost the same information and trying to say, how does this contribute to price? Well, I can't really tell because they're almost the same, so I'm going to give this one a big positive and this one a big negative. And I'm going to tell you that neither can I say are statistically significant because they're so noisy, they're almost the same thing. And so that's a sign of multicollinearity. And the way you could actually diagnose multicollinearity is with this last column. I have mine set up to automatically produce it. If yours doesn't show it, when you look at columns, if you ask for VIF, this is known as the variance inflation factor. And the variance inflation factor ideally is a number close to 1. If it gets as large as 10, it indicates multicollinearity. And notice, in this case, the VIF 4,500 for both of those. Very clear evidence of multicollinearity. The VIF is actually calculated by taking a formula 1 divided by 1 minus r squared, where r squared is the r squared you get by trying to explain each of the x variables as a function of the other x variables. So forget about price here. What it'd be doing for square footage, this VIF number, it says, build a regression model square footage as a function of all these other variables and take the r squared from that regression model. 1 divided by 1 minus r squared. So if that r squared is close to 1, 1 minus the number close to 1 is a very small number. 1 divided by a very small number is a huge number. That's why VIF is high. If there's not much, if you can't explain the, let's say, the features by looking at, by building a model features as a function of all the other variables, then the r squared would be very low, close to 0. 1 minus a number close to 0 is close to 1. It's only a little less than 1. 1 divided by a number a little less than 1 is a number slightly higher than 1. The rule of thumb is that if the VIF is as high as 10, you have a close enough relationship among these x variables that the computer really can't tell you which one is having the effect because they're almost the same thing. And then what it often will do is make one of the coefficients very big and one other one the opposite sign, and it'll tell you that both of them are far from being statistically significant. So you have to be careful. It'd be easy to take a data set and say, let me just put the y variable in and put all the variables in as x variables and just run the regression. The problem is that the x variables, if you have a lot of them, very often might be closely related to each other, and the way it'll show up is the computer won't be able to tell you the effect of each of these separate from the others, and it shows up, the diagnosis of it shows up through the high variance inflation factor. So you should always look at the variance inflation factor, and you can set that under the file preferences. So instead of having to right-click and add it in, if you go to the platforms for fit least squares, that's where you can click the box that says show VIF, and every time you run the regression model, the VIF will automatically be there. You won't have to ask for it. All right, let me show you one other tool here. If you go to fit model and you say I'm going to include price, and I'm going to include these, and let me get rid of my size in square meters since that was an artificially created thing just to show you multicollinearity is a problem. Another way you can run this is instead of what's called standard least squares, you can put in what's called stepwise. And when you put in a stepwise, you get a dialog box. It has a number of settings here. You can do this forward or backwards. If you do it forward, what it does is it starts with no variables in the model and it adds them. It looks for the most significant variable by the p-value, adds it in. Then it says, with that in the model, let me find the next most significant variable, and it keeps adding until it reaches a stopping point, which you can set on what p-value is a cutoff for saying, I'll no longer include this. If you run it backwards, it puts all the variables in. It looks for the one with the highest p-value and drops it out, and then looks at the next highest p-value that remains and drops it out until a stopping point that you can set. So you can explore all the settings, but basically, just to see how it runs, you can go ahead and you click go. It unfortunately, okay. Well, we'll see in a second. I'm not sure if you can do the informative missing with this. It didn't include 49 rows because of missing data. It has included square foot, age, and custom built. This is one of the reasons why I don't like using the stepwise regression, even though it's automated and very quick. Notice it doesn't include features in Northeast because they had really high p-values. But my advice is, even though it has high p-values, they should really remain in the model, but it will automatically leave them out because they have very high p-values. And then if you like that, you can go ahead and click Run Model, and it will run that model. Let's just see if we can do it. I think we can do informative missing with that. So at least it wouldn't be leaving out those data points. So let's see if we click informative missing and change it to stepwise. Yeah, nothing is left out. It's got the age is missing, and it will replace the mean for where age is missing. It still leaves out feature in Northeast, but all the other variables are in there, and you do run model and it will run that model. So when you have a lot of variables, it can be helpful because stepwise kind of scans them all and picks out the most important ones, but it's being driven by, it's not thinking about these variables. So you should be a little bit careful before you just throw all the variables in. Some of them are not going to be, not going to make sense to be putting in the model. You know, you still have to think about what the variables are measuring and what kind of model you think describes them. Although a lot of the techniques we are going to look at are basically black box techniques where we're letting the computer do most of the thinking for us. So there is one more thing to really say about how this model works. Let me get rid of this one. Let me just get rid of the column size in square meters. We don't need that anymore. So this was our best model so far, where age was marked as missing, taken into account as informative missing. And what I want to point out is these variables that are these dummy variables, these 0, 1 variables. If you think about the corner, the way we put this in the model, corner can only shift this regression relationship up or down by this amount of what's estimated here. In other words, corner can increase the value or decrease the value, but it doesn't change the way that any of the other variables influence price. And I'm going to reduce the number of variables here to show you something. Let's do fit y by x. And let's see how price relates to square feet. We've already seen this picture once. But before I fit a line here, let me go and click group by. Let's group by custom built. So what it's going to do is actually separate the data set into custom built and non-custom built and build a least squares regression model for each of those and put them on the same picture. Here are two lines. They look pretty parallel to each other. And in fact, if you look at the slope for the non-custom built, $56 for each square foot. For custom built, $54 for each square foot. What's different is the intercepts. The intercepts are different by about $18,000. This picture suggests to me that I can model this by just putting custom built into the model as a 0, 1 variable, where if it is custom built, you add this much, and if it's not custom built, you don't add that. In a sense, it's more dimensions than just 2 here, but it's creating 2 parallel lines. You have this intercept, and you either add this to it for custom built, or you don't add it for not custom built. The reason why this is different than an $18,000 number is because this is multiple regression. We're taking into account all of these other factors in this model, whereas the other was just fit y by x. We ignored the other variables. But let's try a different picture here. How does price relate to square feet? And let's group it by, instead of custom build, group by corner and do fit line. These lines do not look parallel. In fact, actually, just to see what's going on a little better, if I go back to the data set, let me color or mark by whether houses are on the corner. That's blue and red. The corner houses are the red. The blue houses are not on the corner. What's going on? It looks to me like as houses get bigger, if they're not on the corner, they go up in value a lot more quickly than if they are on the corner. This makes sense to me because a house on a corner, bigger houses are generally more valuable, but the problem with a house on the corner is it's near traffic, and who wants bigger houses? People generally have bigger families, and children playing in the yard on a busy corner is not a good thing. So the same increase in square foot adds a lot less to the value of the home when it's on the corner than when it's not on the corner. It goes a lot faster on the corner, not on the corner than on the corner. The fact that these are not parallel suggests to me that this model that I just built here, where I put corner in, is just a 0-1 variable. It either shifts this relationship up or down. It's not a parallel relationship. It interacts with square feet. To handle an interaction, what you really want to do is you want to take the two variables that might be related, corner and square feet, and add a cross effect, the two multiplied together. So this is known as an interaction effect. The jump will let you put it in even without putting in the separate variables, although to warn you that it's logically, if you're going to put in corner times square feet, you should have corner and you should have square feet both in the model at the same time. For now, just because it's easier to read the output and interpret, I'm going to uncheck where it says center polynomials. Otherwise, the output you get, it centers corner and square feet. It'll be by the mean of the corner and the mean of square feet. It just makes it harder to read the output. So the output's cleaner if you don't center the polynomials. First thing to look at in your output is the term that we added in, corner times square feet. It has a negative sign and it is statistically strong effect. P-value is very low. So that's one way of saying I added something in, this interaction effect. It should be in the model because it is adding explanatory power to the model. It's a variable that is significant. Now to interpret what you're getting, notice being on a corner seems to add $50,683, but that's without square feet. Then each square foot decreases that by $36. So if you had a 1,000 square foot house on a corner, the net effect would be, corner would be 50,000. You would then be subtracting for 1,000, $36,000 for a being on the corner of 1,000 square feet. So that would leave you with 36, about $14,000, $15,000 net positive. And you'd be adding $65 for each square foot of the house. If the house was 2,000 square feet, you'd be adding 50,000 plus for being on the corner, but then you'd be subtracting $36,000, $52,000. So the net effect would be a minus 22,000 because it's on the corner. 2,000 square foot is a reasonable size house. There's probably children in the family that want that house, and that's why it's a negative effect. So what's happening is the effect of square feet has actually two terms. It's $65 plus if it's not on the corner. And if it is on the corner, it's $65 with a plus and a minus $37 here. The net effect is it only goes up by about $30 per square foot if it's on the corner. And if it's not on the corner, it goes up by $65. So there are two different slopes, which is exactly what this picture is suggesting. Oh, no, not that one. It's, I guess I closed it. Exactly what this picture is suggesting. Group by corner. One slope here is about $75, and this one's about $30. So very different slopes. The reason why these numbers, again, are different than what's appearing here is those were only fit y by x. We ignored all the other data. This is taking into account, not this one. This is taking into account all these other variables. So once you account for all these other variables, each square foot for a non-corner house with corner equals 0, 0 times this, 0 is out this term, you get $65 a square foot. But if it is on the corner, you have to subtract almost $37 per square foot for the corner effect. And so very small houses on a corner will be more valuable than not being on a corner, probably because corner lots are bigger and we don't have lot size here. But big houses on a corner actually are less valuable because the corner is not a good location. It's still worth something to have a bigger house, but it doesn't go up very much in value when it is on the corner. So interaction effects can be important. Now, if you think about the model I just ran, this is why even with only a few variables, it can get extremely complex very quickly. What about other interactions? What about even multiple interactions? Maybe being on the corner in the northeast has a different effect of square footage than not being on the corner in the northeast. You can have three-way interactions or more. One useful book I have basically said when it comes to interaction effects, the general rule is you shouldn't include them. Another school of thought is that you should look at all possible interactions, which is almost impossible to do because there are an infinite number of them almost. So I think interactions are not as common to put in. The book's advice is that you should include interaction effects when there's a theoretical reason to be looking for it. It may be what you're interested in actually uncovering, is there, if there's an interaction. When some investigation of data suggests that they may be important, that's what I did here. When I examined some of these pictures, it sure looked like they weren't parallel lines for the corner, so square footage and corner looked like they had an important interaction, whereas custom built and square footage did not seem to have an interaction. So some empirical investigation leads you to think you should put it in there because it looks like it's important. But as a general rule, you don't start off worrying about just because things can get really complex really quickly. You'll have a much richer data set to look at where you have a lot more data points from a healthy real estate data set where you have more room to investigate. But when you only have 117 houses, there's a limit to how many of these you can put in. And that's because I can easily create a nice high R squared by creating a column with a formula. Let's just put in what row number it is. That just numbers the rows. And actually, I don't even need multiple regression. Let me just try to explain the price with this new column that identifies the row number. I think I should just clear the colors because they are somewhat confusing. Oh, actually, I don't want it as a continuous, I want it as a nominal variable. And let's do fit model. Price as a function of the row number. R squared's 1. We just played connect the dots. If you use as many variables as data points, you literally have one exact relationship you can draw between all those points. So it's easy to get R squared to be high by just including enough variables. In fact, as you add variables in, the more variables you have, the higher R squared gets. It has to. I could start adding in the weight of Olympic athletes. It will increase the R squared. Everything you put in your model will increase the R squared. Many of them won't be significant though. So when you look at the R squared, the thing to pay attention to is not the R squared, it's the R squared adjusted, which is adjusted for how many variables you have. So the R squared will keep going up if you add variables, always. But R squared adjusted only goes up if you add in variables that are significant. When you start adding in pure noise variables, even though R squared will keep going up, R squared adjusted will start going down. So don't pay attention to the top R squared, pay attention to the adjusted, and if it goes up, if R squared adjusted goes up, you're probably adding in useful information as opposed to just noise and playing connect the dots. So once you have a model that you like, there's a bunch of things you can save about it. You can save the prediction formula. You can, I'm just going to show 3 of them right now. There's a whole bunch of things that you can look at for more diagnostic, to look at the residuals, where the errors are, how big they are. There are measures of ones that are influential and not. But let's just look at, say, the prediction formula, the mean confidence interval, and the individual confidence interval. So what it does is it goes through and applies that model to every house in this data set. And if you added on blank rows, like you wanted to value a house that had 2,000 square feet, was 5 years old, I can do that. Let's say you had a new house you were interested in, 2,000 square feet, 1 year old, has 5 features. It's not in the Northeast, not custom built, not on a corner. That formula applied to a house would give $133,620. If I had run them, if I put it in first and then run the model, I would get these intervals as well, but they're not formula columns. So in fact, let me get rid of those, do that again. So if you add that in first, and then you go to save prediction formula, save. Oh, I changed the data. It's not actually changing the model, but it's just a warning signal basically saying that you should redo the analysis. And it'll just let me save these. Mean confidence interval, individual confidence interval. Now I'll go back to the data set. These columns are identical, but because it asked me to redo the analysis. So each house, it's giving you a prediction, and it's giving you two intervals, confidence intervals, one for the mean price and one for the individual price. To see how to interpret these, let's just look at the house I added at the end. It's predicting a price of $133,620 essentially. A confidence interval, a 95% confidence interval for that individual house is from 101,000 to 166,000. Quite a wide range. Almost all regression models, no matter how well they fit the data, the individual predictions are going to vary quite a bit because there's a lot of individual variation that can occur. The mean confidence interval will be quite a bit narrower. That only goes from 125,000 to 142,000. And the reason why that's narrower is the interpretation is if you had a lot of houses with these characteristics, on average, what would the value look like? So it's giving you a prediction of an interval for an average house like this. Now, it's very easy it's a slippery slope, because if you really wanted to value this house, let's say this was your house, and you use this model to value it, you say, well, prediction is $133,620, but a confidence interval, well, an average house like this is the confidence interval between these two numbers. But that's not the confidence interval for your house. The confidence interval for your house is this much wider interval. And don't be fooled into thinking that because an average house would have this confidence interval, that's sort of your house. Your house is an individual house, not an average house. So it really would be only useful to use the mean prediction if you had like a whole housing development with these characteristics and wanted to know on average what those houses, what's the value of those houses. If you're looking at an individual house, because individual houses vary in all kinds of other random characteristics that were not included in this model, then you would be looking at an individual prediction interval. And even for good models, the individual prediction intervals will be quite wide, because the fact is there's no miracle here that you're going to come up with a very confident, narrow prediction for something that varies enormously from one individual house to another. So there's the basics of multiple regression, and I think I will stop here.